Yeah, my name is Charley Lineweaver. This is work that I've done with my PhD student, Haiyang Wan, whose image is right there. Unfortunately, he couldn't come. So this is about the devolatilization that leads to rocky planets. And I showed a picture of a comet here because that's a good example of devolatilization of material as it comes closer to the sun. All right, so lots of stars in our galaxy. These are 500 million of the 300 billion in the galaxy. And stars form in the clumps in molecular clouds in the plane of the galaxy. And as you can see from this, when you have a bunch of stars here, particularly the OB stars, they are putting out lots of UV and they're creating these fingers everywhere. So that's an example of the devolatilization in a molecular cloud. So here's an accretion disk, and so here, for example, is a tiny accretion disk, and there's the OB over here pushing away this gas. Here you can see dust is blocking out the star here, and we're getting lots of volatiles along these jets. And here's a picture of what's going on. Essentially, we're removing the gas and leaving the dust. Now, here's another picture. You may have heard that when these protoplanetary disks are there and they're trying to accrete, the star turns on, it's blowing out the volatiles from the interior, and that's essentially what is responsible for the rocky planets that will end up there. And so we have found lots and lots of planets lately, and these are a few thousand from, the red ones are from Kepler, and there are different techniques here. Here's the Earth-like ones. The rocky ones are down here in general, and so we know their mass, we know their period. We also, if we have transit and radial detections, we can get their density. And that's what this plot is about. So this is a slightly older plot, but lots and lots of new planets are being put on here because we're getting more planets that we know both the radial velocity and the transits for. So high density, low density. Now, one example of a devolatilized piece of stellar nebula is the Earth. And so when we plot the Earth compared to the sun, you can see that in some elements, particularly the noble gases, there's very, very little in the Earth in blue. And other elements which are very refractory, you can see that the Earth's relative abundance and the sun's are pretty much identical. Almost, in other words, if we didn't have the sun right there, but we knew the abundances of the Earth, we could look around at all the stars, and by matching the refractory elements, we could figure out which was our mother star. So, now, here are a bunch of stars. Unfortunately, this also is an older plot, but the point is that stars differ in their relative abundances of different elements. So you can see here that now if they're just a line up here, that means they have high metallicity, but the same relative abundances. Down here, if it were just a line, it would be low metallicity, but the same relative abundances as the sun. But you can see that these lines go up and down, and so you get variations of 10, 20, 30% in the abundances of magnesium, calcium, other important elements that eventually will produce the rocky planets around that star. So the name of the game then is to figure out let's be as precise as we can to what is the devolatilization that has produced the Earth from the stellar nebula. And here's a plot. Now, normally Earth scientists, when they look at this, these are the experts in Earth, what they plot here is CIs, everybody's making this mistake, CIs here as a representative of the sun, and they normalize to magnesium, and they get a refractory thing here. This says the Earth and the sun are the same, and then there's this devolatilization here. Typically, they don't use the bulk Earth, they use the primitive mantle. And so we said, oh, you know what? We're going to do a better job than these Earth scientists. First of all, we're going to put error bars on the bulk Earth, and we're going to include the core, and so we're going to get the elemental abundances of the Earth with error bars, and that has never been done before. It's been almost done, but we used what has been done before and did a better job of combining things, and we think we have the best bulk elemental composition of the Earth ever, and you should use it in your future if you're interested in what the Earth is made of. We did the same thing for the sun. Let's go forward here. So here's what's plotted on the y-axis is abundance normalized to aluminum now, and aluminum is much more refractory than the silicon and the magnesium that are usually used, so therefore you don't get the artificial increase in you don't get an enrichment of the refractory elements. And here what's plotted is the Earth, the concordance bulk Earth in the blue, and then we've also done what has usually been done is we did the primitive mantle, dividing it into these types, different element types, and you can see that flat here, and there's a line here. So I said, well, you know what? We got a flat here and a line here. Let's fit this. Has it been fit before? Kind of, but not really. So let's do the best job of fitting this line, this devolatilization trend, as we call it. And when you do, well, first of all, there's a difference. When you look at plots like this, make sure, are they normalizing to CI chondrites, or are they normalizing to the sun? There's a difference. A lot of things are the same, but there's very important differences. For example, here are the CI chondrite abundances, here are the solar photosphere abundances, and you can see it's basically the same, except for lithium is being burned in the sun, and all these have been depleted in CI chondrites. Because CI chondrites, they have a lot of refractories. It's the most volatile, rich, sometimes called the primitive meteorites that we use as a proxy for the sun, but in terms of these elements, it's a really bad proxy. So let's continue. So highly volatile elements, there are 9, and they're depleted in the CIs and are well determined in the photosphere. 13 elements without photospheric abundances are well determined in the meteoritic abundances. Primordial lithium is burned in the sun. And so the whole idea is, how do you combine photosphere with CI measurements to make the best measurements for the sun? And that's what we did, and here's our method. Now, Lauder's 2009 did something very similar. Here's how she divided up those elements and combined them. Here's how we did. This is the elements that are based only on the photosphere, elements based only on meteorites. Lauder's loves meteorites, so she put most of them here. But we averaged them. This A stands for average. So we averaged all these elements because both photospheric and meteoritic abundances are available for those elements. Okay, so when you do that, you get a plot that looks like this, but you can see it better down here. The blue is the photosphere, the red are the CI chondrites, and the yellow is the way we've combined them together to get the best estimate of the protosolar abundances. And that's what we need, because the protosolar abundances are what was devolatilized to produce the Earth. Okay. So along the way, we figured, hey, why don't we do the X, Y, and Z? These are the mass fractions in hydrogen, helium, and everything else. And it's interesting to know that over the last 3 decades, this Z, the fraction of material in the sun that's not hydrogen, helium, has been going down from 1.89 all the way down to about 1.40 right here. Now, when you plot up the sun, so here's the sun, and the blue is the Earth, and you can see that they're up and down, up and down. Some of them are identical, and some of them are devolatilized. Some of them are really devolatilized. And when you plot that as a function of condensation temperature, notice that this is linear condensation temperature, not log. You get something that looks like here. Oh, it's identical, identical, identical. Oh, it goes down a little bit, and then it has this line here, and then it swoops down here. A blow up of this area is right here, and you can see that it's up and down, up and down, up and down, and then it starts to go down right about here. So if you normalize to silicon or magnesium, you're pumping this all up artificially, and then you say, oh, it's enriched in lithophiles. That's just an artificial product of your normalization. Okay, so let's fit this line. Now this is pretty much the main result, and that is we have here the sun, the new values of the sun as I described. We have here the bulk Earth, so we really are comparing the Proto-Sun with the bulk Earth. And then we have this line here, and what's an interesting feature is, where does this line cross this line? And that we spent some time to get this, and it's 1391 plus or minus 15 Kelvin. Here's the blow up of that right here. Moving along. Now let's compare what I just showed you to previous closest things. And there are some things here from Cargill and Lewis 93, Palm and O'Neill 2014, McDonough 2014. And basically they had this enrichment that I told you about. When we renormalize theirs to aluminum, for example, that brings them all down here. And then here's our 1391, and here are their values right here. So there's some outside the error bars of ours. So we think we have the most precise measurement of some temperature that I don't think has a name. I've asked lots of earth scientists, what's the name of this temperature? So we just call it the devolatilization temperature, or the break temperature, or the critical temperature, beyond which you have flat here and then go down here. Now, let's look. Now notice in this plot here, we have 500 is the lowest value of the condensation temperature. For the next one, and this is a log value of Tc, condensation temperature. But now we're going to go further down, and you can see that this blue line, which is established here, we've just extrapolated it out here. Now, one thing you could do when you extrapolate it out here, you can say, oh, look at that. the mercury in the Earth looks like it's overabundant compared to this line. What could be wrong? Well, what's wrong is that there is no measurement of photospheric mercury, so we just assume it's been from the CIs, and when you do that, you get a miscalculation here. But I have 5 minutes, okay. So if you say, you know what, let's not assume that the mercury, this pretty volatile thing, is the same in CIs in the Proto-Sun, then you bring this down to here, and you get a much more accordance. Oh, you're into question time. Okay, you're into question time. Okay, I will stop in about a minute. I guess the point is that when you extrapolate here, you get some noble gases which don't fit that line very well. They're all depleted here. And we suspect that the condensation temperatures of O and C are not right because Lauder's condensation temperatures are due to an equilibrium gas that's cooling and at equilibrium. And I suspect we're talking about really non-equilibrium. In other words, we have big chunks of material that's coming into the accretion disk that is not it's not like an onion. Well, it's not at equilibrium, let's just say that. And it gets sublimated. And what else do I want to say? And C, well, they're probably different values for TC, for O and C. And what else? So we also looked at this in terms of the CIs, and we got some kind of volatilization temperature for CIs. As you can see that they're very close to the sun and then they diverge right here. And I'm running out of time. We recalibrated to CIs, just have a look at it from another way. And we get the sun going up, the CIs normalized to the 1. And then the last slide is, to first order, the Earth is a devolatilized piece of the solar nebula. Similarly, rocky exoplanets are almost certainly a devolatilized piece of the stellar nebula out of which they and their host stars form. By comparing the compositional differences between Proto-Sun and Earth, we have quantified the first-order devolatilization pattern that can be used to estimate the chemical composition of rocky exoplanets around other stars because we have those other stars' elemental abundances by doing spectra. Thank you.
Charlie, very interesting talk. I definitely want to talk to you and get your slides afterwards.
Casey, who are you?
Oh, I'm sorry. Terry Liss, Johns Hopkins University Applied Physics Laboratory, old friend of Charlie for many years. I would be a little worried about your devolatilization temperatures you're assuming for carbon, hydrogen, oxygen, and nitrogen. As you know, Chon elements can combine into many different materials, right, all of which have hugely or vastly different evaporation temperatures. So you may want, maybe that's part of your problem. It isn't just bulk carbon, it isn't just bulk oxygen that you're evaporating.
Exactly. I completely agree with you. That's why we have these little, but what we can do is figure out what those condensation temperatures are. For right here, for example, we can say, okay, let's pretend that they fit. What does that say about the different elements in them? Now that's a little bit like, well, I suspect that will give more accurate distributions of these elements rather than the ones that were put in by Lauders when she did her calculation.
Steve Dash, ISU. This is really fantastic. It's a very much needed thing, so I'm very excited also to get a preprint or something. I wanted to do the same thing, and what I ran into is that for siderophiles, they're all in the core, and we don't know what's in the core. And for refractories, very often they actually just assume the abundances are the same as chondrites. How did you get around those problems?
Well, one thing is, the first thing we had to do was figure out what the mass fraction of the core is. There are about four things that, 4 papers have been written, but Earth scientists are convinced that they don't need to put error bars. So we said, oh, we have 4 numbers for the mass fraction of the core, so you need to know, was it 32, is it 33, is it 31? And we looked at that carefully and combined results, and then you had to use a new gravitational constant too, because the total mass of the Earth has changed because big G has changed a little bit. So these are tiny, well, I would say significant, but usually detailed differences. Also, you're right that it's model dependent, but there are about 7 models. So what we did is say, well, there's a model, there's a model, there's a model for what the composition of the core is. And then we just said, okay, let's take the upper and lower error bar and say that's the uncertainty in the composition of the core, which we then add to the primitive mantle. You're right, the primitive mantle is everybody knows about it because it's more accessible, but there are many, many ways to model, not get great estimates for the core, but the best ones that exist, and that's the ones we used.
Okay, we'll talk
with error bars that are legitimately reflect how much the people who are modeling the cores think they know about it. In other words, don't just, oh, we can't do anything about it. I think that's just that's what everybody in their sciences community has done so far because they don't keep track of their error bars.
Let's have Charley.
Oh, we have to go. Okay.
Yeah.
Thank you.